Good morning, class. We are recording the session. We are covering chapter 5 integrals, sections 5.1 to 5.3. Basic integration formulas. Again, there are a few pages have been discussed already. The method of exhaustion is used to find the area under a curve, just the way it was used to find the area and the circumference of a circle when they didn't have the formula for it. So in this example, we use the function, we cut it into 4 pieces. So the interval of A to B is cut into n interval in general, giving rise to delta x, or the fixed width of a b minus a over n. When we chose n equals 4, then b minus a divided by 4. We have the fixed width, but what about the height? The height can be the left endpoints, the right endpoints, or anywhere in between. We used the left and right endpoints, and the area was evaluated to be between 3.75 and 5.75. We did exactly the same thing with more rectangles. More specifically, we used n equals 8, and it gave us a better approximation, as now the area is between 4.1875 and 5.1875. An approximation gets better as n gets larger. So that was using the Riemann sum, and the Riemann sum is an approximation of the area under the curve of a function f of x between the interval of a to b, as long as the function is a continuous function and a positive function. When we take the limit and we let n go to infinity, it becomes the actual area under the curve. So instead of using the Riemann sum, we use FTC. There are 2 of them. One of them, we evaluate the integral of f of x dx from a to b using the antiderivatives. So this is the anatomy, if you will, of the integration symbol, the lower and upper limits, the function itself, dx, and the fact that that's a dummy variable, because if you use any variable, it makes no difference. It results in the same thing. This is called a definite integral because it results in a number. We looked at this example using the area. As you can see, it's a horizontal line. When you draw, you end up with a rectangular shape where the area is the height times the width. We end up with b minus a. We also did it using the antiderivative and the fundamental theorem of calculus. The same thing happened here. However, we are looking at the net area or the signed areas, because the top one dealing with the positive function is considered positive. The red one below the x-axis is considered negative. So we subtract the area from the red one from the green one. Finally, on this page, we used FTC. The integral of a to b f of x dx equals f of b minus f of a, to evaluate each and every one of them. And the reason is you really don't want to go with the area unless you have no choice. And the point was, what happens when the area fails? The calculus will always work. So this is the FTC, the integral of a to b f of x dx. Find any antiderivative and evaluate it at the upper limit. F of becomes capital F of b, and the lower limit capital F of a. The difference is the answer. The reason you don't use a constant, because even if we did, it wouldn't make a difference. Let's look at this example. First, we have to find the antiderivative for this function 5x squared minus 4x plus 2. Using the power rule, the first one results in 5 thirds, 2 plus 1, 5 thirds x cubed minus 4 over the exponent here is 1 plus 1. So minus 4 halves x squared plus 2x. We don't need a constant because we are evaluating from 0 to 2. So again, 5, the exponent is 2, add 1, 5 thirds. This one, again, I will show you, this one is negative 4. So you say negative 4 divided by the exponent is 1. So 1 plus 1 results in negative 2x squared plus 2x. So let's plug in. We are plugging in the upper limit 2 and the lower limit 0. Needless to say, when we plug in 0, we get 0. This is 8 minus, this is 2 times 2 squared, that is also 8. So what you're looking at, 5 thirds times 8, 40 thirds. Minus 8 plus 4 gives you minus 4. Take a common denominator. The answer becomes 28 thirds. 28 thirds. We want to evaluate this, and I hope you remember, even for differentiation, the first step is an algebraic step. We do the division. We cut this into 2 fractions. The first fraction gives you 4 v to the power of 6 divided by v cubed is 4 v cubed. Here's the second one, everybody. So minus 3. So the first step is algebra. Now we are going to find the antiderivative. I hope you see how this thing works. 4 divided by the exponent plus 1, v exponent plus 1. Simply put v to the power of 4. Think about what is it that you differentiate to get to 4v cubed. So v to the power of 4 minus 3 gives us negative 3v. We are evaluating from 1 to 2. And again, anytime you have doubts, go back, differentiate this one. It should give you 4v cubed. Okay, class. Now, plug in the upper limit 2. We get 2 to the power of 4 minus 3 times 2. And then plug in the lower limit 1. This is 2 to the power of 4, or 16, minus 6. This is 1 minus 3, which is negative 2. With the negative in front, becomes positive 2. They add up to 12. We are evaluating the integrals, class. I hope you remember we did this without evaluation from 1 to 3. In other words, we did the indefinite integral and we added a constant. So I'm going to quickly remind you. Again, you cut it into 3 fractions. This one gives you 1. This one gives you minus 7x over x squared, or minus 7 over x. This one gives you plus 2 over x squared. So we cut it into 3 fractions. This is our algebraic step. Now, to integrate, the first one is very obvious. One, you look at this one and you decide to go with x, right? The variable is x. So 1 gives you x minus 7. 1 over x gives you natural log. What did we do here? So let's look at this last piece. We wrote this one as a 2 x to the power of negative 2. In other words, we used the power format so we could integrate or anti-differentiate. So 2 divided by negative 2 plus 1 x to the power of negative 2 plus 1. The numerator is 2, the bottom is negative 1, so negative 2 x to the power of negative 1, and we ended up with the following. Of course, previously we had a constant because it was an indefinite integral. Now we don't. We are evaluating from 1 to 3. So this is the only calculus step. So this is the only calculus step. Now we are going to evaluate again using algebraic techniques, everybody. Let's plug in the upper limit 3 minus, let's plug in the lower limit 1. So we are just plugging in number 3 and then number 1. At this point, we have to evaluate, so let's do that. So this one, 3 minus 7 ln 3 minus 2/3. The second one, ln 1 goes to 0 and minus 7 times that is also 0. Then we have 1 minus 2, which gives us negative 1, and that gives us positive 1. So we are looking at number 3, number 1, which is 4 minus 2/3, which is 10/3. I'm assuming we can easily add up numbers with a fraction. Remember, when we subtraction is a form of addition. And we keep it as minus 7 ln 3 because that's an exact answer, everybody. That's an exact answer. So we keep it intact. Precise answer. Here's the next one. Again, I'm looking at the question we did before. The difference is now it's a definite integral, it results in a number. So 1, we look at dt, be very careful. So we want t, not x. Normally we use x. Take a look at this one. 1 gives you x. Now, the derivative of cosine is negative sign, but the integral of that is positive sign. And we don't need a constant because we are evaluating from 0 to power of 2. Let's plug it. Pi over 2 plus sine pi over 2 minus 0 plus sine 0. Sine of 0 is 0. The whole thing is 0. Simply pi over 2 plus sine pi over 2, and sine of pi over 2 is 1. Here's the next one, everybody. Again, we change this to x to the power of 1/2, so we can use uh, the power rule. So first we use our algebraic techniques, we put them together as such. 5x to the power of 3 halves plus 3x to the power of 1 half. Now we use the power rule. 5, okay, we're going to divide by the exponent plus 1. So we're going to divide by 3 halves plus 1, x to the power of 3 halves plus 1. Same thing here. We're going to divide this by the exponent plus 1. Plus 3, we're going to divide by 1 half plus 1. Remember, this is n plus 1, and x to the power of 1 half plus 1. We don't need the constant because we are evaluating. Again, I am using simply the following rule, class. The antiderivative of this one is 1 over n plus 1 x to the power, and we don't put the constant here because we are evaluating from it. So 3 halves plus 1, use a different color. 5 halves. So what is 5 divided by 5 halves? 2. 1 half plus 1. 3 halves. What is this? Also 2. 3 divided by 3 halves. 5 divided by 5 halves. Both of them are 2. Again, we are done with calculus. Remember, the calculus step is this one with the asterisk only. Plug in number 4, evaluated. Plug in number 1, evaluated. So let's do that, everybody. Let's plug in number 4. Let's plug in number 1. We want to see what we end up with. So this one is the square root of 4 to the power of 5, 2 to the power of 5, which is 32. So that's the first one. 2 times 32 is 64. So this is all elementary algebra. Square root of 4 cubed, which means 2 cubed, which is 8. 2 times that is 16. What I'm using is the following, class. The a to the power of m over n is the nth root of a to the power of n. That's what I'm using. When we go to the second one, 1 to any power is 1. So this is 1, this is 1. So we get 2 plus 2, which is 4. So minus 4. That's the answer. Put them together. We end up with 76. So I hope you realize the importance of the algebra here. There are a lot of algebraic steps. Here's the next question. Water flows from the bottom of a storage tank at this rate, R of t is 200 minus 4t liters per minute. That's a rate. We want to find the amount of water that flows from the tank during the first 10 minutes. So what we are looking at is the rate. Therefore, here's what we should pay attention to. If capital R represents the amount of water, then R prime or lowercase r is the rate that it flows. So this is the rate, and the antiderivative represents the amount of water. That's the idea. And therefore, we can find the antiderivative and find the amount of water, or we can do just the fundamental theorem of calculus, because that also represents what we call as a net change theorem or accumulated change. So the amount of change can be calculated using the rate and integrating it from A to B. In this case, we want for the first 10 minutes. So from 0 to 10. That's what we want. From 0 to 10. This is known as net change or accumulated change theorem. We can do that. So integration will give us here 200t minus 2t squared. Evaluation from 0 to 10, if you plug in 10, we are replacing the t with 10. 200 times 10 gives us 2000, minus 10 squared is 100, times 2 is 200. And when we plug in 0, we get 0. So I'm going to write this minus 0, which is 1800 liters. Why is that? Let's go back to R of t and take a look at this unit here, liters per minute. That was the rate, liters per minute. So what is the amount of water? The units would be in liters accordingly, in liters. We could find, okay, I'm going to look at the second method in the next example. The second method, I'd like you to try this at home. Find capital R of t, which practically we have it here and a constant, which is, okay, from here, it's 200t minus 2t squared plus a constant with the initial amount at 0. There is nothing that has been given to us, with R of 0 being 0, which gives you the constant, and then calculate R of t. Try this at home, you'll see what you get. So to make some sense out of this second method, in this example, I'm going to go through both methods. So many fish grow in a way which is described as one Bertalanffy growth equation for a fish that starts life at a length of, this is the starting point, 1 centimeter and has a maximum of 30 centimeters. This equation predicts that the growth rate, again, this is the growth rate of 29 e to the power minus x centimeters per year, where x is the age of the fish. How long will it be after 4 years? So what do we do now? We're going to go through the same process as the previous example. This is the growth rate. That means the derivative function in essence. So if capital L of x, because we are looking at the length, represents the length, then this represents L prime of x, or dl dx, or the growth rate. So L of x represents the length of a fish at any age x, then the growth rate is what we have here. And the amount of increase in length can be calculated as follows: the accumulated change or the net change theorem can be used here. So we're going to integrate that from 2. We want it for the first 4 years from 0 to 4. So 29 divided by -1. Remember, when you differentiating, you multiply by -1. When you're integrating, you divide by it. In this case, it makes no difference. Division as well as multiplication by -1 gives you the same. So -29 e to the power minus x, evaluated from 0 to 4. Plug in 4 instead of x and plug in 0. So -29 times e to the power minus 4 minus e to the power of 0. I want you to know that you really have to use a calculator here. Of course, this is 1, but you have to use a calculator for e to the power minus 4. And we are going to have with a bunch of decimals. So this represents the amount of growth. But remember, the fish that starts life with the length of what? 1 centimeter. So add 1. We have to add 1. And why are we going with 1 decimal? They're asking for 1 decimal here. By the way, the function is an approximation itself. So it's really the number of decimals is not that important here. But always carry many, many decimals unless you're asked otherwise. Here's the second method, as I discussed in the previous example. Instead of finding the amount of growth and then add to the initial size, whatever it was, the initial size happened to be 1. Let's find the function that represents, the length of the fish. So let's find L of x. And since we've done most of the work here, take a look. We've done most of the work. We have L of x equals this from 0 to 4. But if we are not evaluating from 0 to 4, that is the same thing plus a constant. So the same function plus a constant is the answer. However, we have this initial value problem, if you recall when we discussed the concept of initial value. The length of a fish was 1 centimeter to begin with. So L of 0 is 1. So you are going to replace L of x with 0 and L of x with 1 and x with 0, which means the following. So we're going to say this is, if this is 1, by the way, e to the power of minus 0 or 0 makes no difference, makes it 1. Okay. So -29 plus c, so c must be positive 30. So L of x becomes -29 e to the power minus x plus c. C is replaced with number 30 because we want the age after 4 years. We want L of 4. And if you evaluate L of 4, you get exactly what you got here.